Hello everyone, welcome back to another video with Mr. Coder. And in today's video, I'm going to show you how to solve BAUDELAIRE, the easy version. So the easy version of the problem is that every node is adjacent to node 1. So that means it's like a star graph, basically. So this problem is interactive. So BAUDELAIRE is very rich, so he bought a tree of size n, rooted at some node. Additionally, each node has either a value of 1 or -1. And in this version, every node is adjacent to node 1. However, please note that node 1 is not necessarily the root. So don't assume that 1 is the root. So Calvin Nerd wants to get the tree, and he doesn't know which node is the root, and he doesn't know the value of the nodes either. However, he can ask BAUDELAIRE questions of two types. So the first type is let f of u be the sum of the values of all nodes in the path from the root of the tree to node u. So then Calvin may choose any integer k, and k nodes u1, u2, all the way to uk, and then receive the value f of u1 plus f of u2 plus f of u3 all the way to f of uk. So it's just basically the sum. So notice that it can be 1 as well. So notice that it doesn't need to be some sort of sum. And also the second query is 2, and then you just have an integer u, and BAUDELAIRE will toggle the value of node u. So specifically, if the value of u is 1, it will become -1 and vice versa. And that's like a permanent change. And Calvin wins the tree if he can guess the value of every node correctly, the values of the final tree after performing the queries. And it has to be within n plus 200 total queries. So can you help him win? So this is an interactive problem. So just it's a question mark for a query and an exclamation mark for a answer. And then notice that I won't go over this, but just flushing. I'm in C++. I use cout.flush. You can use endl. Uh you can use endl, or you could use cout flush like in a different way. Or you just comment out this thing. They all work. But I don't like getting idleness limit exceeded and not knowing, so I just do all of them basically. So yeah. So this problem is hard to actually visualize. So I'll just give you an example of what the graph will look like. So for example, this is node 1 right here to the right of my screen. 2, 3. So they're all connected in node 1. So 4. So now you can actually use like a star graph. So they'd all be connected in node 1. And you're given all the adjacencies, but they don't really even matter just because you already know they're all going to be connected to 1 with no other adjacencies. So then I'm going to erase these since these might not actually be the values. And notice that 1 might not be the root. So then if just say this is 1, -1, 1, 1 or something like that, then and we let this one be the root. So if this one's the root, then if you want to find f of u, so if you want to find it of this one, then it's just going to be equal to 0. If you want to find it of this one, it's going to be 1, since it's the sum of all three of these. This one is also going to be 1. So then, and if you do a query of type 2, then this one turns into -1, which means this one is no longer 1. It's actually going to be -1. So that's how you can change it, and that's also query 1. So this problem isn't clear at first how to actually solve this problem, but it's actually there's a trick that you can use. So basically, something you should first notice, and it's a key observation, is that if we go back here to 1, 2, and 3, so just say this is the star graph still, even if it doesn't look like it. If this one's a root, right? Then how do you find the value of this one? Well, it's since you can't really actually check the sum of an individual one. So then you can just do f of this one minus f of this one. So you can just do f of this one minus f of this one, and then I'll get you the value of this. So which one would be this one? Is it always going to be 1? No, it'll just be the parent of it. So since there's a root, that means there's going to be a parent. So it's going to be f of u minus f of the parent. So then that means if you did this one, it would be f of this one minus f of, and since if 1 isn't the root, then 1 will be connected to the root since it's connected to everything else. So it's going to be f of 1 minus f of root. So notice that it's just going to be this one minus that one. So that's basically a key observation. But then notice that where does it, so then you might think, oh, is it just f of x minus f of 1 for all x's besides 1, and then you can just do you can find 1 in a different way or whatever. No, it's not, because f of x minus f of 1, that works for every single one of them, unless if x is the root. If x is root, then it would actually be negative of this, which is just f of 1 minus f of x. So yeah, that's basically a key observation you get here. So then you get this adjacent, it doesn't really even matter, but the star is centered at node 0, and you need to find the parent of node 0, which is node 1 in the problem statement. So that's important, so then you can figure out which one you need to adjust when we actually do the end queries later. So you binary search, and how do you binary search it? Well, you do that's the key reason why there's this value k here instead of just doing u1, as there's only one u, because that hints at binary searching, especially if it's n plus 200. You think about binary searching. So you have half of them as equal as the query for the sum of all the f of u, and then afterward you change the value of node 1 because it's the center of everything. And then again, you check those same values. And then if the parent is not in there, if the parent of the root is not in there, then you would then it would be exactly equal to 2 times the number of elements, because then the center one, node 1, is changed from either 1 to -1 or -1 to 1, which is 2 increase. So it would be 2 increase for each one. So it would have to be exactly that, the absolute value of the differences, which means that it's not in, so then you'd update L to be greater if you originally did it from L to mid inclusive. So then you'd increase L. Otherwise, if it ends up being in the range, then you set the result to be mid, and then r equals mid minus 1. So then if it's not in the range, you already set the result. And notice that you should always set it to be equal to 0 to start, because that's going to be, if it's not in the range to start at any time, then it's always just going to be 0, which is the node you're currently at. So after these queries, which will take 3 times the logarithm of, in this case, 3 times the logarithm of 1,000, which is like 30 queries. And then afterward, then you can just get the answer. So and make sure you store SQ, which that's how I get the single query. So 1, 1, x plus 1. Make sure you do 1 indexing for the queries. And then for if you query 0, make sure you don't keep querying it, otherwise that'll be 2n, which is way too much. So you have to reuse answer of 0. So then for each I, you set from 1 to n minus 1, you set that answer to be the single query of I minus answer of 0. And then you can finally update the answer of result. That's just going to be the single query of the result. And then that's because you need to update it, since this won't be correct. So then you get for res, if res is not equal to 0, which is just the result, or which is the root basically, or that's just what I use as a return value for a binary search, then you need to subtract ans 0 minus equal to ans of res, because you basically need to do the current minus the parent. That's how you get the current. And then you can just print it out. So yeah, that's basically how you solve Baudelaire, the easy version. So tips here is just notice n plus 200. of course you need to do n queries to actually find out the sums or whatever. So 200 really hints at uh it really hints at binary search since or some sort of cutting in a certain way. So then you can limit the query since 2n of course doesn't work, which 2n would be 2000. So you basically have a maximum of 1200 for any n of equal to 1000. So yeah, that's basically how you solve Baudelaire easy version. Thank you for watching this video. If you like this video, please like and subscribe, and I'll see you in the next one. Bye.